All right, guys, it's now time to move on to chapter 5. Chapter 5 is going to be dealing with sequences and series. So we will be doing first sections 5.1 through 5.6 here. So, of course, we are starting with section 5.1. We are going to define what a sequence is. Sequence is where I'm going to be starting out. Let's define what that is. An infinite series AN is an ordered list of numbers of the form A1, A2, up until forever and ever and ever. So, what do I mean? Okay. So, first things first, a sequence is a list. That's pretty much it. You're not doing anything with them, it's just a list. So, like, an example would be like, first of all, the brackets like this mean like the set of. So, the set of all terms that look like 1 over n. This is a sequence because it's just a set. It's just a list, right? I'm not doing anything. I'm just going to list them out. So in this case, A1, my first term would be 1 over 1, which is 1. My next term, A2, would be 1 over 2. My next term, A3, would be 1 over 3. So basically, I'm just going to plug in, right? So then for A4, I would plug in a 4 and make it 1 over 4. For A5, plug in a 5, 1 over 5, on, and I'm just listing them out. That's what this is. It's just a list, okay? We write it like this so that we don't have to actually list everything out because that would be impossible, right? Because it just keeps going and going and going. So writing it like this tells me it's a list of 1 over 1, and then 1 over 2, 1 over 3, 1 over 4, 1 over 5, on and on and on. That's what that is. Again, it's just a list. Just a list, but I don't write it as a list because you can't, because there's a ton of them, right? So I write it like this instead. The subscript n is called the index. For each an, I call that a term. So then this is my first term, second term, third term, fourth term, on and on. Sometimes sequences are defined by an explicit formula, and what that means is kind of like this, right? I know I can just plug in 1 and get A1, and then I can plug in 2 and get A2, right? So like in this case, the function is 1 over n because it's saying what I plug into to get my terms, okay? So that's pretty clear. But sometimes, in other cases, sequences are defined by using a recurrence relation. In these, one term, or maybe more, of the sequence is explicitly there, and then every other term is written in terms of the previous term. So what I mean by that is instead of having like this where it says plug in 1 and I get 1, plug in 2, I get a half, plug in 3, I get a third, and that kind of thing, it's going to tell me how to use my first term to get the next term. So like it would say something like A1 is equal to 2, and then every other AN is going to be like 4 minus 3 of my previous one. Okay, so it's stating the first term, and then after that, I'm going to use this guy to get my next term. Okay, so like for A2, then I would do 4 minus 3 times the previous term, which would be A1. They give me that, so this is going to be 4 minus 3 times 2, which is 4 minus 6, so negative 2. So A1 is 2, A2 would be the negative 2. Then I could use that to get A3, because it would be 4 minus 3, the previous term is A2. So then I would do 4 minus 3 times negative 2. That's 4 plus 6, which is 10. So then my next term is 10. And then I could keep going on and on and on through that. So I could either be written like this, which is the most common way, or it could be written like this. Again, this is an explicit formula. This is a recurrence relation. Either way. Okay, there are two special types we have that we see a lot of. The first one is arithmetic, excuse me. In which case, right here, the difference between two terms is always the same. Okay, so then that's like an example of an arithmetic sequence would be like 1, 3, 5, 7, 9, 11, on and on, because there's always two between them, right? From 1 to 3, that's two places. From 3 to 5, that's two places. From 5 to 7, that's two places. On and on. So this is arithmetic sequence because of that. So an example of one right here, example of an arithmetic sequence. Consider the sequence 3, 7, 11, 15, 19, on and on. Notice that the difference between any two terms is 4, right? Because between each gap is 4, right? Therefore, this sequence can be defined by the recurrence relation. A1 is equal to 3, because that's my first term. And therefore, every other AN is going to be the previous term plus 4. Again, because I'm adding 4 to each time. So I know my first term is 3. After that, we add 4 each time. Now, notice that A2 would be 3 plus 4, right? Because I'm going to add 4 for every term. And so A3 would be 3 plus 4 plus another 4. And then A4 would be 3 plus 4 plus 4 plus another 4. And I would do that on and on and on, right? So for A3, that's 3 plus 2 times 4. For A4, that's 3 plus 3 times 4. Therefore, I could write this as AN is equal to 3 plus 4 times n minus 1. Because for A3, I added 4 twice. For A4, I added 4 three times, right? So it's 3 plus 4 times n minus 1. If I simplify that, I get 4n minus 1. So the two ways I could write the sequence 3, 7, 11, 15, 19, on and on. I could write that as the recurrence relation. A1 is equal to 3, and AN is equal to 3 plus, not 3, AN minus 1, the previous term, AN minus 1 plus 4. I could write it like that. Or I could write it as the formula AN is going to be equal to 4n minus 1. Because if I plug in a 1, it would be 4 times 1 minus 1, which is 4 minus 1, which is 3, which is right. For A2, plug in a 2. That's 8 minus 1, 7, which is right. And it would go on and on. And again, how I got that was I noticed that I start for A2, I start with my first term, which is a 3, and add 4. For A3, I'm going to do 3 plus 2 4s. For A4, I'm going to do 3 plus 3 4s, which gives me this 3 plus 4 times n minus 1, which is 4n minus 1. Another special type we have is geometric. In these, the ratio between every two pairs is the same. So, an example of that would be like if we had 2, 4, 8, 16, 32, on and on. Notice from every term, I'm going to do 2 times 2, which gives me 4, times 2, which gives me 8, times 2, which gives me 16, times 2, and then it would just keep going on and on and on. Since I'm doing times 2 for every one of these, that is geometric. Again, because I'm doing times the same thing for all terms. So an example of that, consider the sequence 2, negative 2/3, 2/9, negative 2/27, 2 over 81, on and on and on. Notice that the ratio between any two terms is negative 1/3. Because if I did 2 times negative 1/3, that's negative 2/3, which is our next term. If I did negative 2/3 times negative 1/3, that would make it positive. 2 times 1 is 2 over 3 times 3, which is 9. So 2/9. If I did that times negative 1/3, that'd be negative. 2 times 1 is 2. 9 times 3, 27. On and on. So because of that, this is geometric. So I can use the recurrence relation right here. My first term is 2 because it says so, right? My A1 is 2. And then I know it's negative 1/3 to my next one, right? So for my next term, I would do negative 1/3 times the previous term for all of them, because that's what I did over here, right? So this is the recurrence, because I know my first term is 2, and to get my next term, I times it by negative 1/3. So now let's use that and get the formula. Now notice that if I wanted to find A2, I would do negative 1/3 times 2, because 2 is my first term, right? It starts out at 2. Times the negative 1/3. To get A3, I would take that and times it by another negative 1/3. To get A4, I would take that, what I just got, and times it by another one. So A3 is negative 1/3 squared times 2. A4 is negative 1/3 to the third times 2. And then it would go on and on and on. So what I can see here is that AN is equal to 2, because they always had a 2, because that's my first term, right? Times negative 1/3 to the power of n minus 1, because for the fourth term, I did to the power of 3. For the third term, I did to the power of 2. For term number 2, I did to the power of a 1, right? So this is it. So that's just a general idea of how I'm going to find what the formulas are with these. So let's do some examples now. Example number 1, for each of the following sequences, find an explicit formula for the nth term of the sequence. So I want to find a formula for these. So let's see if I can find a pattern to give us the formula. Again, for example number 1, we're finding the formula. The first one's going to be the sequence negative 1/2, 2/3, negative 3/4, 4/5, negative 5/6, on and on. So let's see. What's the first thing we see here? I go negative, positive, negative, positive, negative, which means I would go positive, negative, positive, negative. So how I'm going to then write that is with a negative 1. However, since they don't all have those, I've got to be really careful with what my power is. So notice I have one on every odd term. I have it on my first term, my third term, my fifth term, and it would go on and on and on. So on every odd term, I'm going to have the minus sign. So now think about this. What power must negative 1 have to be the negative? Well, the power has to be odd, because if I had like negative 1 squared, that's negative 1 times negative 1, which is just 1. If I did negative 1 to the fourth, that's negative 1 times negative 1 4 times, which is still 1. So in order for it to be negative, my power has to be odd. Since it's happening on every odd term, I can just make my power n. Because then for the first term, it would be a power of 1, which works out. For the third term, it would be a power of 3, which works out, and so on and so forth. If this was positive, and then it switched, and then positive, and then switched, so that every even term had it, I would do n minus 1 because I want my power to be odd. Okay, but it's on every odd term, so we can just write it as n. So now let's see what's happening with the terms here, okay? Well, notice on top I get 1, 2, 3, 4, 5. So on the top of my first term, I have a 1. For A2, my top is 2. For A3, it's a 3. For A4, it's a 4. For A5, it's a 5. So the numerator is just n, right? It's just n. Again, my first term, it's a 1. For A2, it's a 2. For A3, it's a 3. So it's just n on top. Now on the bottom, let's see what I can find there. Well, notice it's the numerator plus 1, right? 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. So the denominator is just the numerator plus 1. Since we already said this was n, we know my denominator is n plus 1. And there we have it. Again, I'm just looking for the patterns, is what it is. Just looking for the patterns. Example B, we're going to do the same thing. 3/4, 9/7, 27/10, 81/13, 243/16, and on and on and on. So again, I'm just looking for what the pattern is. That's what I want to see. So let's see if there's anything I can notice here. So hit pause and think about this. See if there's a pattern you see. So now, notice on top, I have 3, 9, 27, 81, 243. What do all of those have in common? All of those are power of 3. 3 to the first is 3. 3 squared is 9. 3 to the third is 27, on and on and on. So the numerator is going to be a power of 3. Well, what should my power be? Well, my first term, I get 3, which is 3 to the first. My second term is 9, which is 3 to the 2. So for A1, it's 3 to the 1. For A2, it's 3 to the 2. For A3, it's 3 to the third, and on. So it's just to the power of n. Now the denominator is going to take a little bit more thought because it doesn't really follow that same pattern, right? But what do we see here though? For each term, I'm adding 3, right? I'm adding 3, I'm adding 3, I'm adding 3, adding 3, and it would keep going on and on. So let's see what I can do there. So what I know is that A1 is just equal to 4 because it says 4, right? For A2, I would take that 4 and add 3 because it's plus 3, right? For A3, take what I got on the last one and add another 3. For A4, take what I got for the last one and then add another 3. And you would just keep doing that on and on and on. So what this means is that for every AN, I'm taking 4 and I'm adding 3, but how many times? For A2, I added it once. For A3, I added it twice. For A4, I added it 3 times. So this is n minus 1. Calculate that. 4 plus 3n minus 3, which gives me 3n. 4 minus 3 is plus 1. So the denominator is 3n plus 1. Remember, if anything isn't making sense, sense, let me know. I will be happy to help you out. All right, for example number 2, what we're doing is for each of the following recursively defined sequences, find an explicit formula for the sequence. So the same thing, but instead of a list, I'm going to give you the recurrence relation. So we're still doing the same thing. Find the formula. Our recurrence relation is that A1 is equal to 2, and every other AN can be found by doing -3 times AN minus 1. So let's see what happens here. So then I already have that A1 is equal to 2. So let's find A2. For A2, I would do -3 times my previous term, which was 2. For A3, I would do -3 times the previous term, which we said was -3 times 2. For A4, I would do -3 times the previous term, which we just said was -3 times -3 times 2. So I can kind of see what the pattern will be here, right? For every AN, I'm taking the number 2. There's always a number 2. So the number 2. And I'm going to times that by -3. But how many times, right? For A2, I did it once. For A3, I did it twice. For A4, I did it 3 times. So it would be to the power of n minus 1. Just like that. For example, B, our recurrence relation is that A1 is going to be 1/2, and then AN is going to be A to the n minus 1 plus 1/2 to the n. So let's see what happens there. So for A1, it already says 1/2. For A2, the previous term, which is 1/2, plus 1/2 to the second. For A3, the previous term, which we said was 1/2, plus 1/2 squared, plus then I would do it 1/2 to the third. So for the fourth one, 1/2 plus 1/2 squared, plus 1/2 to the third, plus 1/2 to the fourth, 1/2 to the fourth, and on and on and on. So let's see here if this is really a helpful thing, right? Notice over here, there was a pattern, right? -3 to the second, -3, -3, -3. You know, that's not happening here though, right? I'm always adding another term. I'm adding something that's new, right, to every one of these. So I can't do this one like we did this one. Again, because I'm always adding something that's new over here. So it doesn't really help us. Whereas over here, everything is pretty much the same thing, right? Over here, I'm adding 1/2 squared, which isn't up here. Then I'm adding 1/2 to the third, which is not here. Then I'm adding 1/2 to the fourth, which isn't here. So I'm constantly adding a new thing. So there's no pattern I can see there, okay? So instead, let's try listing these terms out and seeing if that helps us, right? So my first term is 1/2. My next term would be 1/2 plus 1/2 squared is 1/4. 1/2 plus 1/4 is 3/4. Then this one would be, this was from our last one, which is 3/4. I'll write it down here. 3/4 plus 1/2 to the third, which is 1/8. 3/4 plus 1/8 is 7/8. So it'll be 7/8. Then for A4, we already said this is 7/8. 7/8 plus 1/2 to the fourth. 1/2 to the fourth is 1/16. 7/8 plus 1/16 would be 15/16. And let's see if we can see a pattern from there. Well, notice the denominators are 2, 4, 8, 16. So then I could guess my next one would be 32 because these are all powers of 2, right? So the denominator is always a power of 2. This is 2 to the first, 2 squared, 2 to the third. So this is just 2 to the n. And now let's see what's happening on top, right? Well, notice here, they're always one less than the denominator, right? 2 minus 1 is 1. 4 minus 1 is 3. 8 minus 1, so it's just always this one less, right? So take the denominator and subtract 1. And there we go. Once again, remember, if anything doesn't make sense, let me know. Totally fine, just let me know. All right, so now let's look at something. We're going to relate a concept we already know to this, okay? Given a sequence a(n), if the terms a(n) become arbitrarily close to a finite number L, as n becomes sufficiently large, we say a(n) is a convergent sequence and L is the limit of the sequence. In this case, we write the limit as n goes to infinity of a(n) is equal to L. If a sequence a(n) is not convergent, we say it is divergent. So basically what I want to know is as n gets really large, do my terms get closer to something, right? So look at this one we just did. 1/2, 3/4, 7/8, 15/16. My next term would be 31 over 32. My next one would be 63 over 64. My next one would be 127 over 128, and keep going. Notice these terms are getting closer and closer to 1. So this sequence a(n) converges to 1 because my terms are getting really close to 1. Whereas with this one, my terms would be 2, -9, -6, sorry. I was like, that sounds right. So 2, -6, 18, -54, on and on. It'll just grow and grow and grow and grow and grow. So I'm not going to get close to one thing. So this one diverges. So let's look at some examples to see if we can make this make some sense. Oh, and then the theorem right here pretty much is saying what I just said. Consider a sequence a(n) such that a(n) is equal to f of n for all n greater than or equal to 1 if there exists a real number L such that the limit as n goes to infinity of fn is equal to L, then the limit as n goes to infinity of an is equal to L. Basically what it means is I can just take the limit of this stuff right here and it'll tell me what happens. That's all that that says. I know it seems like a lot of words to like not say very much, but that's it. So let me show you what this means. Example number 3. Example number 3 says for each of the following sequences, determine whether or not the sequence converges. If it does, find the limit. So for example number 3, we're going to find the limit, if there is one. First example is going to be the sequence 5 minus 3 over n squared. So all I'm going to do is do the limit as n goes to infinity of that. That's it. That's all I've got to do. The limit of 5 is just 5. 5 is 5, doesn't change. If I plugged in a number that's really big in the denominator here, something really big squared is really big, right? 3 over something really big is really small, right? So think about it like 3 over a million. That's really small, right? 3 over 10 million, 100 million, a billion, on and on. It's getting smaller and smaller and smaller. So the limit of 3 over n squared is going to be 0. 5 minus 0 is 5. So this sequence converges to 5 because the limit is 5. Example B, the sequence 3n to the fourth minus 7n squared plus 5 over 6 minus 4n to the fourth. Let's look at this one. So again, I'm just taking the limit as n goes to infinity of the function. This is a concept from Calculus 1. Basically, since my n is going to get really, really big, I only care about the largest term for each part. The largest term on top is n to the fourth. So I'm going to take 3n to the fourth. On the bottom, it's negative 4n to the fourth. We'll look at what happens here. N to the fourth cancel out. The limit of 3 over the negative 4 is negative 3/4. So this converges to negative 3/4. That's what it means. Example C. Sequence 2 to the n over n squared. So again, that means we're going to take the limit as n goes to infinity of 2 to the n over n squared. For this one, we've kind of got to think a little bit which one is going to grow at a faster rate, right? So on top, I would end up with 2 squared is 4, 2 to the third is 8, then 16, then 32, on and on. N squared, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and then 6 squared would be 36. Notice that the numerator is growing at a faster rate, right? Because then it'd be 128 over 49, on and on. So the numerator is growing at a faster rate, which means this is going to infinity. Therefore, this diverges. I didn't get a number there, so it's going to diverge. This is going to diverge. For example, D, I'm actually going to erase this. This is going to be the sequence 1 plus 4 over n to the n. So we're taking the limit as n goes to infinity of 1 plus 4 over n to the n. This is a concept from Cal 1. I'm going to describe it this first time, and then every other time I'm going to assume you are going to remember this. And so here I go. If n gets really big, 4 divided by n gets really small. So with this inside stuff, just approaches a 1. 1 to the power of something really big is something we called an indeterminate form in Cal 1. So when that happens, there's something else I've got to do. First things first, what I don't like about this is the power. So I want a way to bring the power down, okay? So where in math have I learned of something where I can bring my power down to the front? That's in a logarithm, right? So let's set this just equal to L, and I want to find L. Let's do the natural log of L. Again, because if it's in a logarithm, I can bring my power down to the front, right? So this is the natural log of the limit as n goes to infinity of 1 plus 4 over n to the n. Remember, since the natural log is continuous, I can switch those. This is, again, a concept from Cal 1. Make this ln 1 plus 4 over n to the n. Since I have a power inside of a logarithm, remember I can bring it down to the front. That's a logarithm rule. So that's n times the natural log of 1 plus 4 over n. Whenever I have an indeterminate form, I want a fraction. So how I'm going to do that is I want to bring n to the denominator and write it as to the power of -1. So n to the -1. Now that I have it in this form, I can use a concept from Calculus 1, L'Hopital's rule. I'll write it up here. L'Hopital's rule, that's what I'm going to do right here. Remember what this says is that I can take the derivative of each part. So the derivative of the top, the derivative of a natural log is 1 over that stuff. So 1 over 1 plus 4 over n times the derivative of the inside stuff. The derivative of 4 over n is negative 4 over n squared over. Then the derivative of n to the -1, remember that's like saying 1 over n, is negative 1 over n squared. Well, the really nice thing here, negative and the negative make a positive. 4 over n squared over 1 over n squared just leaves us with a 4 on top. So this becomes the limit as n goes to infinity of 4 over 1 plus 4 over n. Now, as I plug in stuff that's really big in here, this is going to be really big, which makes this whole thing really small. So this becomes just 4 over 1, which is 4. But I can't stop just yet, though, because that is the natural log of L. I want just L. So if the natural log of L is equal to 4, remember the natural log is log base e, so this base is e to the power of 4. That's L. So this converges to e to the 4th. Now, am I going to expect you to do this every time? No. In Cal 1, after we did this, remember we figured out, oh, this is actually really nice, because if I ever have the limit as n goes to infinity of 1 plus a number over x, I'm using too many n's, hang on. X over n, that's what I meant. X over n to the n. This is just e to the x. So since I had a 4 here, that's e to the 4. If I have just a 1 there, that's just e, and on and on and on. So write this down. This is important. We're going to use this several times. But again, this is how I get that, is right here. All right. This next concept was also something we did in Cal 1. Consider a sequence AN and suppose there exists a real number L such that the sequence AN converges to L. Suppose f is a continuous function at L. Then there exists n such that f is defined for all values AN for n greater than or equal n, and the sequence f of AN converges to f of L. That's a lot of words. What it's saying is exactly like what I did at this step right here. Exactly what I did here. Since the natural log is continuous, I can switch these. That's all that says. So looking at an example, example number 4 says determine whether the sequence cosine of 3 over n squared, determine if that converges, and if so, find the limit. If it does, it may not. So what I want to do is take the limit as n goes to infinity of cosine 3 over n squared. The cosine may make this seem harder than it really is, okay? But since it is continuous, I can just switch those. So I can bring the cosine out front and do the limit as n goes to infinity of 3 over n squared, which isn't that hard, right? Because as n gets really big, this whole thing gets really small. So this becomes cosine of 0, which is 1. So this converges to 1. Same thing with example number 5. We're going to do the same thing with the sequence square root 2n plus 1 over 3n plus 5. See what happens with that. So again, we're going to do the limit as n goes to infinity of this. Well, the square root makes it look harder than it really is, but since it is continuous, I can bring it outside and do the square root of the limit. So again, I want to look at the largest term on top, which is 2n, and the largest term on the bottom, which is 3n. Cancel out the n's, and that ends up with just the square root of the limit is 2/3. So this is going to converge. It converges to the square root of 2/3. That's what I have. This next thing is another thing from Cal 1. I'm just going to restate it here. The Squeeze Theorem. Consider sequences an, bn, and cn. Suppose there exists something n such that an is less than or equal to bn, which is less than or equal to cn for all n greater than or equal to that big N. If there exists a real number L such that the limit of an is equal to L and so is the limit of Cn, then Bn must converge to L. So what does this mean? Notice here Bn is between An and Cn. So if An and Cn go to the same point, Bn must also go to that point. Because once again, Bn is between An and Cn. So like An is somewhere up top. This is An. Bn is less than that, and Cn is less than that. Well, what it's saying is if An and Cn approach the same point, Bn must also approach that point because it's got to be between them, right? So that's what I have. So if I can find a sequence smaller and a sequence larger that approaches the same thing, then I'll be good. So like for example A, let's see what, or for 6A, let's see what happens to the sequence cosine of n over n squared. Now trying to do the limit of that would be hard because cosine, what it does is it just goes up and then down and then up and then down and then up and then down. So it's really hard to say what happens as n gets really big, right? Because again, it's just going up and down. So instead, I can use this squeeze rule, okay? Remember, cosine's got to stay between -1 and positive 1, right? So since cosine, I'll just write it like this, is between -1 and 1. Remember, because the graph goes like this, -1 and 1. We know that -1 over n squared is less than or equal to cosine of n over n squared is less than or equal to 1 over n squared, because cosine is between -1 and 1. Well, notice here the limit of the smaller one, n gets really big, the whole thing gets really small, 0. And then the limit of the larger one, once again, the bottom gets really big, so the whole thing is really small, 0 there too. So since 0 is on the left side and on the right side, we know that the limit of cosine of n over n squared must also be that same thing. So this converges to 0. Again, because I found one smaller and one that's larger, that both converge to 0. Another example, this is 6b, the sequence -1/2 to the n. Once again, taking the limit of that would be hard because it's going to switch from positive to negative to positive to negative, on and on and on and on and on, right? So instead, let's find one that's always smaller. Well, the negative sign could be out front. So that's always smaller. And then also, it could also be positive, which would be a larger one. So let's see what's happening right there. So the limit as n goes to infinity of -1/2 to the n. So then this would be -1/2, -1/4, -1/8, -1/16, -1/32. Those are getting smaller and smaller and smaller and smaller. So this is going to 0. And then the limit of the right side, once again, this would be 1/2, 1/4, 1/8, 1/16, 1/32, smaller, 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 0 there too. So since this is between them, we know this also converges